Hi everyone, and welcome to this presentation on achieving low carbon solutions using concept. My name is Emily Halliwell and I'm a structural engineer at the Concrete Centre. In this presentation, I'm going to introduce you to Concept version 4, a free tool that enables designers to quickly carry out concept designs and compare different concrete frame types. I will then go through some worked examples showing how concept can be used to quantify the carbon savings that can be made through optimized designs. I'll finish by talking about how you can access free tools and guidance on low carbon design from the Concrete Centre. Concept is a free tool that enables designers to compare 13 forms of reinforced concrete construction. The tool calculates cost, construction time, and embodied carbon for each option to allow designers to select the optimum solution for their project. The designs are based on our economic concrete frame elements to Eurocode 2 book, and Concept provides initial sizes for structural elements. We're now going to talk you through how to use Concept. Concept is an Excel spreadsheet, and when we first open it, we arrive at the welcome page. This gives an overview of how to use the tool, as well as assumptions and limitations of the spreadsheet. If we click Go to Notes, this gives more detail about the design information assumed in Concept. From the welcome page, we click Start to input our project data. So we start by inputting our building geometry. The first thing we do is set the number of bays in each direction. Then we define the span lengths for each bay. And then we can define the story heights, and there are options here for how this is defined and for our edge columns. Once geometry has been entered, you click Refresh Layout, and the image showing the bays will update. And then once you are happy with the geometry, we can click Go to Loads. On the Loads page, we set the number of stories using these arrows. We then set the material properties. The concrete strength for slabs and beams is a fixed value, but there's a drop down here for column strength, and you can also input the ground bearing pressure if this is known. We then input the floor loading, and there are example loads given on this load spreadsheet for different building types. We then click to optimize, and you will see the spreadsheet running. Once that's finished, you can click Go to Results, or you can also go to the rates page here if you want to alter the default values. The rates page includes information on unit costs, embodied carbon per meter cubed, and program data. Recommended values are provided, and these are based on information from industry. And these are the default values given on the left-hand side in the spreadsheet. Users can then input their own values here based on information available from the project team, such as the contractor or quantity surveyor, or based on the concrete specification. This is the results page. At the top of the table, you can click to rank the options based on different parameters: cost, program, and embodied carbon. This will then sort the schemes based on this parameter. So here I've sorted by total cost. The traffic light color coding on the results page allows users to visually compare different parameters. Below the table, you will see some notes on what each comparison is based on. So for the embodied carbon, this is calculated for modules A1 to A3 and includes the slabs, beams, columns, and ground floor slab, but does not include the foundations. If you scroll down on the results page, you will see this graph plotting embodied carbon against cost. And this is another way to help select the optimum solution for your project. Now that we've seen how concept works, I'm going to talk you through some worked examples showing how we can use it to quantify embodied carbon savings. On screen, I've included some of the key methods for reducing embodied carbon and optimizing structural design. The worked examples will look at some of these methods and the impact they can have. The following examples are based on typical building parameters, and I will give percentage savings for these typical cases. However, the savings will vary for different buildings, types, and sizes. In this first example, I am looking at the impact of grid spacing. I've compared two buildings with the same footprint, which is 36 by 36 metres. One has columns spaced at 9 metres and the other columns spaced at 6 metres. It's a 10-storey building with residential loading, and we can see that if we use 6-metre spans instead of 9 metres, for a two-way slab, we can reduce the depth from 195 millimetres to 125 millimetres, which would result in a 32% reduction in embodied carbon. In this second example, I've looked at the impact of reducing the imposed load on the structure. This example is based on an office building with 4 bays in each direction, each spanning 6 metres. The building's 8 stories high. A typical office floor might have a load of 5 kilonewtons per metre squared, which would be made up of an imposed load of 4 kilonewtons per metre squared and an allowance of 1 kilonewton per metre squared for partitions. However, if we instead use the loading recommended in the UK National Annex of Eurocode 1, which is 2.5 kilonewtons per metre squared, and we make the same allowance for partitions, we can reduce the depth of the slab and beams and use smaller columns, leading to a reduction in embodied carbon of 9% for the two-way slab option. Concept allows us to compare 13 forms of slab construction. In the previous two examples I've shown, I've just compared the options with the lowest embodied carbon. However, in this example, where I've looked at spans of 10 metres and a 6-storey building with office loading, I have looked at these different options. So we know that flat slabs are popular and may be the option that we initially consider. However, using concept, we can see the potential reductions in embodied carbon that we can make by selecting a post-tension flat slab instead. This gives a 17% reduction in embodied carbon and a 6-day reduction in construction time. To reduce embodied carbon further, we could adopt a two-way slab, which gives a 23% reduction in embodied carbon, although this would add almost 3 weeks to the construction time. In this final example, I'm considering how we can alter the material specification to reduce embodied carbon. Concept contains recommended values for the embodied carbon of different materials. For in-situ concrete, these are based on data from BRMCA and for a generally available CEM2 mix. For hollow core planks, the values are based on an EPD from British Precast, and for reinforcement, they are based on a UK CARES EPD. Although concept contains recommended values, users are free to enter their own data based on EPDs and other sources of information. So for my final example, I've looked at a 5-storey building with typical office loading. It's 3 by 4 bays, each with a span of 7.5 metres. And here I've looked at the impact of altering my concrete specification. So at the top we can see the default values based on a CEM2 concrete, and below that we can see alternative reduced values using a CEM3 concrete. By specifying a different concrete mix, but without altering our designs in any other way, we can achieve reductions of around 25 to 30% in our embodied carbon. Just to note here that I've only altered the values for C3037 and C3240 concrete. If you are using higher strengths for your columns or have specific data for hollow core planks, then these values can be amended as well. So in these examples, I've shown the impact of changing one of the highlighted parameters at a time. However, we can, of course, use these options in combination to achieve greater overall savings. If you would like to use Concept for your projects, it can be downloaded for free from our website using the details on screen. On the download page, you will also find a how-to webinar, which includes step-by-step guidance for using Concept and a full worked example. There is also a how-to guide to help you get started. Concept is based on our Economic Concrete Frame Elements to Eurocode 2 guide, which is available to purchase from our website and includes full details about how the structural sizes are calculated. If you're looking for ways to reduce the embodied carbon of the concrete you specify, we have a free guide on specifying sustainable concrete. We also have free guides on concrete frame buildings and material efficiency, which provide guidance on efficient designs and the different framing options. To conclude, this presentation has provided an introduction to Concept and other guidance available from the Concrete Centre to help designers develop low carbon solutions. We've seen how Concept allows designers to quickly develop and compare concept designs and quantify the carbon reductions that can be made through optimizing the design. If you have any questions about this webinar or any of the tools and publications discussed, please contact me at ehalliwell@concretecentre.com. Thank you.